Now, the next thing I'm going to talk about is what's called calorimetry. Okay? When we have materials that are placed into contact with each other, if we leave them long enough, they're going to come into what we call thermal equilibrium. Meaning, if we put something cold next to something hot and we leave them next to each other long enough, the thermal energy from the hot object will transfer into the cold object, and eventually they will equilibrate at some temperature in between the starting cold temperature and the starting warm temperature. That process of thermal energy transfer goes from hot to cold. I know it makes you feel like you're getting cold when you go outside, but actually what's happening when you go outside is that you are giving away your heat to the outside world. That's causing you to become colder. So that process, we call that a transfer of heat, and we use symbol Q that has to do with how much energy transfer happens between two objects. And Q is related to a variety of things. One of them is M, the mass of the object that you have. And again, if you think about something like, a very large mass, very hard to heat up a very large mass, right? Very hard to cool down a very large mass. So the mass is relevant here. Also, how much there's a coefficient here called the specific heat. And that is different depending on the material you're talking about. Water's got a specific heat, or heat capacity, same basic thing. Water's got one, aluminum's got a different one, lead's got a different one. Every material you can think of has some heat capacity, and those are different. And the other thing that dictates how much energy is going to flow is how much the temperature difference is between where the object started and where the object ends up. Okay, so basically how much energy flows into that. And what ends up happening is that we would say that if we have two objects, let's say we have Q hot and we have Q cold. Okay, so one of these comes in hot, the other comes in cold, we put them in contact with each other. Well, if you add them together, that plus that, it's going to be zero. Because all the energy, if you're assuming that you can take this system and isolate it from the outside world, all the heat energy that's in this one, the only place it has to go would be to this one. And so when you add them together, this one cools down, this one heats up, and you get a total of zero. And the other way that this is commonly written would be just like this, saying, the heat and the cold are opposite, so that, different signs. Okay, but anyway, I like this form because then if we have more than two objects, we just add them all together. We have to decide which ones are losing energy, which ones are gaining energy. But if we add them all up, we will get a total of zero. And each one of them is going to have this type of formula here. Now, it's not quite that simple. As long as they're not changing phase, that's going to be their formula. So, for instance, when you have something that melts, or you have something that that vaporizes, there are additional terms that come in, because when something melts, if something's sitting at 33 degrees Fahrenheit and it drops by 1 degree, for a little while it's sitting there at 32 degrees Fahrenheit as water. And then it becomes 32 degrees Fahrenheit as ice. There's no change in temperature there, so there can't be a change in temperature for that term. So terms like the ones that are affected by melting and vaporization, those are additional terms. Now, primarily, I tell you to deal with things in MKS units. And the MKS unit here is the joule for energy. But I will tell you, in this particular case, it is more convenient to use calories, and I'll tell you why in a minute. 1 calorie is equal to 4.186 joules, okay? The reason that calories are better in this case is because water is defined as its specific heat is defined as being precisely 1 that you would put in here for a change of 1 degree and a mass of 1 gram, that's 1 calorie, okay? And so, since we'll deal with water a lot, it's convenient. See, some water equals 1. It's convenient to use calories for the units here, and typically in physics books, and ours is the same, all these values that they give for specific heats, etc., they give them both in calories and joules because of the fact that water usually comes up. Now, why does water usually come up? Well, if I want really good thermal contact between two objects, I could take a chunk of aluminum and a chunk of lead, and I could try to shove them together. The fact of the matter is there's going to be some microscopic breaks in between the two of them. I can't get them into true good thermal contact. But if I put them both in water, the water will swirl all around them, get into all the little nooks and crannies, etc., and I will get good thermal contact. So as a general rule, when I deal with calorimetry, water will be one of the components that I will be dealing with. And as a result, this fact that there's a 1 in the calculation in a lot of places makes that a much easier calculation to do. And you'll see this when I do lab later.